Right. Bismillahirrahmanirrahim. Assalamualaikum and very good evening. So first of all, thank you for joining the class tonight. I'm sorry that we have to do a replacement class at night because I have some work commitments that I have to attend to. So we have to cancel the class. So we need to replace the class so that we can finish the syllabus. Okay. So this will be the final, the last subtopic for chapter 4 and for the whole course of dynamics lah. So now we are in subtopic impulse and momentum, right? So similar to the previous subtopic, which we talk about work and energy previously, work and energy. So work means one definition of work, and energy has another definition. So same goes for impulse and momentum. So who knows what is the meaning of impulse? Anyone can remember what you have learned in physics maybe? So what does it mean by impulse? When you say impulse in physics, what does it mean? Anyone remember? Impulse. Anyone can guess perhaps what is the meaning of impulse? Okay, I give a clue. Impulse is force multiplied with something. What is the parameter that force is multiplied with?
Time.
Yes, exactly. So to give an impulse or to calculate impulse, you multiply the force with time. Okay, force multiply with time will give you impulse. So force has the unit of Newton, all right, and time has the unit of seconds. So when you calculate impulse, the unit for impulse will be Newton seconds, right? So it is basically force multiplied with time. This is for, of course, this is for linear lah. Okay, this is for linear. All right. So when we talk about rotation motion, remember in rigid body dynamics, we not only have linear motion, but we also have rotational motion. So for rotational motion, it is similar. When you have force for linear, for rotational, we will have moment. Okay, we will have moment and also multiply with time. Okay, so for rotational motion, it is moment times time, and for linear motion, it is force times time. Okay, so moment has a unit of Newton meter, right? Newton meter, and time has a unit of seconds lah. So for rotational motion, you're going to have the unit of Newton meter seconds. Okay, so that is Newton meter seconds. Okay, so that is impulse. All right. What about momentum? Anyone remember what is the meaning of momentum? Anyone? Momentum. So we have defined that impulse is force multiplied with time for linear, and for rotational, it is moment multiplied with time. What about momentum? Anyone? Momentum. Okay, let's give a clue. Momentum is now mass multiplied with something. What is the parameter that mass is multiplied with to give you a momentum? No idea? Okay, so momentum is mass times velocity. Okay, mass times velocity, right? So mass is kilogram lah. Mass is kilogram. Mass is kg. Velocity is meter per second, right? So that will give you momentum. M times V, mv. Okay, and again, this is for linear. This is for linear motion, right? So for rotational motion, what do we have? Rotational motion. If linear, we have mass, then what do we have for rotational motion? Any idea? What is the sibling of mass? If linear is mass, then rotational, it's going to be mass moment of inertia. Mass moment of inertia, which is Ig. We have calculated Ig a few times in the class. Mass moment of inertia. Okay, so mass up here is m, right? Mass moment of inertia is Ig, and velocity is v. All right. So mass moment of inertia, the unit is kg meter square, right? And multiplied with, now when linear you have velocity, then for rotational you're going to have angular velocity. Okay, angular velocity. So angular velocity is basically omega. Angular velocity is omega, and the unit for angular velocity will be radian per second. Right. So that is basically the definition of impulse and also momentum. Okay. So now, similar to work and energy, previously we have the principle of work and energy. Okay, the principle of work and energy that we have been using in the class. Okay, principle of work and energy. This states that T1 initial kinetic energy plus the total work done to move from position 1 to position 2, total U from 1 to 2 is equal to the final kinetic energy at position number 2. So this is the principle of work and energy. Okay, for impulse and momentum, there is also a similar principle. Okay, there is also a similar principle. So we can also write the principle of impulse and momentum. Okay, the principle of impulse and momentum. All right. The principle of impulse and momentum. So before we go to the principle of impulse and momentum, let's derive how the principle, where the principle comes from. So basically, the main equation that is used to derive the principle of impulse and momentum is the Newton's second law of motion lah, that you have learned in chapter 2, which is F equals to ma. So basically, we have F equals to the mass times acceleration. Okay, F equals to ma. And then we know that acceleration is also the change of velocity dv over dt. Okay, A is equal to dv over dt. We have learned this previously. V is equal to ds dt. A is equal to dv dt. So F equals to ma can also be written as F equals to m times dv dt. Okay, so we can change this a little bit, m times dv dt to become d over dt. We take out the velocity, multiply with m times v. Okay, multiply with m times v. Okay, we take out the v here from dv dt, bring to the left hand side, and it becomes d per dt times m times v. Okay, notice that mv here. What is mv? We have learned previously. Mv is basically the momentum. Okay, mv is the momentum. Okay, so this is where the momentum comes from. Okay, mv is the momentum. Now, what about if we bring this dt here? We bring dt to the left hand side, to the f to the side of the force. We bring dt to the side of the force. So what will happen is we will have F times dt is equal to d times mv, dmv. Okay, F dt is equal to dmv. So dmv means the change of momentum lah. dmv means the change of momentum, which means that this is mv2 minus mv1. Okay, dmv is basically momentum at time 2 minus momentum at time 1. Okay, dmv, the change of momentum. So it must be momentum number 2 minus momentum number 1. And then on the left hand side, now this d has gone. This d on the right hand side has gone. We have turned this d into mv2 minus mv1. So now what do we do with this dt? We need to get rid of that also. So to get rid of that, we need to put integration of f. Integration of f dt. Okay, integration of f dt. This is from time 1 to time 2. Okay, so integration of f dt, this side here, will give you ft. Will give you ft. And what is ft? We have discussed previously. Ft is basically the impulse. The impulse, right? And mv is the momentum or linear momentum lah. This is linear momentum. Okay. So from this, what we can get is that we can get a principle of linear impulse and momentum. So we need to put another word here, principle of linear impulse and momentum, because this equation focus on linear motion only. So what we have here is, if you look, we can bring this minus mv1 to the left hand side and it will become positive lah. Okay, so if we do that, we will get mv1 plus the integration of f dt, which will give you the impulse ft, is equal to mv2. Okay, so when we if we look closer to this, let's highlight this. Okay, if we look closer to this, you will see that this is the initial momentum, initial linear momentum. This is basically the total impulse, and the final term at the back is the final linear momentum. Final linear momentum. Okay, so you can see that this principle of linear impulse and momentum is identical to the principle of work and energy. For the principle of work and energy, we have initial kinetic energy plus total work done is equal to final kinetic energy. And for principle of linear impulse and momentum, you have the initial momentum plus the total impulse is equal to the final momentum. Okay, so that is the principle of linear impulse and momentum. So we can expand this. So let's copy this. Okay, let's copy the whole thing. Okay, I will copy this and bring it here. Paste. Okay, so this principle of impulse and momentum, principle of impulse and momentum, right? we can extend this into several equations. So the first one is this linear momentum. We can get the equation for both x and y axis. So for x axis, you have m times vx1 plus the total fx dt, total force in x-axis dt, is equal to m times vx2, right? So this is the principle of impulse and momentum, principle of linear impulse and momentum in x-axis. Now for y-axis, we can write the same equation, m times vy1, right, plus the total force in y-axis, integration of fy dt, is equal to m times vy2, right? So this is initial impulse, initial momentum in y-axis plus the total impulse in y-axis is equal to the final momentum in y-axis. Okay, we have another one which is for rotation. Okay, for rotation. Okay, for rotation. Okay, for rotation, we can generate similar equation like previously. We know that the sibling of mass is Ig. So you can write here Ig, all right, times V, V1. V1 is the velocity. So for rotation, we will have omega 1, okay, plus for impulse, we have force for linear. For rotation, we will have the moment. So integration of moment. Now we measure Ig here about point G. So the moment will also be about point G. So mg dt, okay, mg dt is equal to Ig times omega 2, right? So right here, we have basically three equations lah. We have three equations that we can use to calculate problems in this final subtopic. So first one, we have the principle of linear impulse and momentum in x-axis. So this is the principle of linear impulse and momentum in x-axis. Okay, so basically both lah, these two are the principle of linear impulse and momentum. So let's bring this to the center, okay, like that. And the second one, we have the principle of linear impulse and momentum in y-axis. And the last one, we have the principle of angular impulse and momentum. So this one is angular. So the third one is the principle of angular impulse and momentum. All right. Okay, so this is basically what we have so far. MVX 1 plus total impulse in x-axis equals to MVX2. And we have MVY1 plus impulse in y-axis equals to MVY2. And then IG omega 1 plus MGDT plus the integration of MGDT is equal to IG omega 2. All right. The other thing is when you refer to the textbook, they also use different symbol. For example, the symbol for let's go to this another page. So when you have linear momentum, the symbol used is L. L is basically equals to M times V lah. L equals to M times V. For angular momentum, this is for rotational lah. Angular momentum, the symbol used is H. Okay, H is equal to I, depends on where is the point that you calculate lah. So normally we will calculate Hg, and this will be Ig times omega, right? So the principle that we have previously, this we can write it in terms like, for example, L1 plus the integration of f dt is equal to L2, for example. So L is referring to mv1 lah. L is referring to mv1, and L1 is referring to mv1, and L2 is referring to mv2, right? Same goes for the angular impulse and momentum, principle of angular impulse and momentum. We can write this as H1 plus the integration of moment mg dt, or you can write this as hg1, okay, hg1, because we need to know where is the point that we calculate. So this is equal to hg2, right? So this is basically ig omega 1, and hg2 is ig omega 2. Okay, this is just for your information lah, because you can also use this. This is more practical to use. You use mvx, mvy, and also ig omega. But sometimes in the textbook, you will find the principle of angular impulse and momentum, or principle of linear impulse and momentum is written this way: L1 plus f dt equals to L2, and also hg1 plus mg dt equals to hg2. Okay, so before we go to example questions, do you have any questions so far on the explanation of the principle of impulse and momentum? So this is basically what we will be using throughout the class. Any question? Okay, if there's no question, let's proceed to an example problem. So let's zoom in and read the question. 60 kg wheel has a radius of gyration about its center O, KO equals to 300 millimeters. So you know by now, when radius of gyration is given, you know that this object is non-homogeneous. So the radius of gyration is used to calculate the mass moment of inertia IG. Okay. If it is subjected to a couple moment M equals to 3t square, okay, the moment is given in a function of time, which means that, what does it mean? M equals to 3t square. So when time equals to 1, what is the value of moment? When time equals to 1, what is the value of M? Moment is equal to what? When time equals to 1. You just substitute the value of time equals to 1 in the function of moment. So you will get moment equals to 3. Okay, when time equals to 1, moment equals to 3. When time equals to 2, moment is equal to 3 times 2 square. 2 square is 4, 3 times 4 is 12. Okay, and so on. So you can see that the moment is changing with the time. Okay, so what is the question here? Determine the angular velocity. So what we want to know is omega, angular velocity, when t equals to 4 seconds. Okay, so this is the difference between the impulse and momentum question and also work and energy question. Work and energy involve distance. So for example, you will be asked to determine angular velocity after the wheel has rotated a few revolutions or after 10 meter. That is the type of question for work and energy. So it will involve distance. Okay, work and energy involve distance. When it comes to impulse and momentum, it will involve time. So you can see here, when t equals to 4 seconds. So that is what we want to know. Okay, now let's go back to this. We have three equations. So let's copy this first and put in the page of the question. Okay, let's paste it here. All right. Okay. So by reading the question, you know that what you want to calculate is the angular velocity. So by looking at these three equations, the angular velocity can only be found from this equation, from the rotation punya equation. That is one. Number two is that you can see that the object here is having a rotation motion. So the wheel will stay in this place, but it will rotate. Okay, it will rotate in clockwise direction. So for this question, what you need to do is you don't have to use the equation for the linear impulse and momentum in x and y axis. So what we want is we want to know omega 2. This is what we want to know. After 4 seconds, after t is 4 seconds, that is omega 2. And there is another clue here, starting from rest. Okay, bila it says starting from rest, it means that omega 1 here is equal to 0. Okay, the value of omega 1 is equal to 0 because it starts from rest. So that is the clue that you have lah. Okay, so what do we do here? Now let's calculate first Ig. Okay, let's first calculate Ig. Right, so Ig is, for this case, is equal to m times, or in this case, the center of gravity is written, is given by O. So let's use IO instead lah of instead of IG. Let's use IO. So IO is equal to m the mass times KO square. Right. So the mass is 60. Okay, the mass is 60. KO is 300 millimeter. You convert it to meter, divide by 1000, you will get 0.3 meter and put square there. So you will get the value of IO is equal to 5.4 kilogram meter square. Okay, kilogram meter square. That is IO. Okay. Now, so we have now the equation of IO. We can substitute all the equation, the value of IO in the equation of principle of angular impulse and momentum. So we have here IO omega 1 plus the integration of T1 to T2 mg dt is equal to MO dt, because now we are using point O as the center of gravity. So let's use MO dt is equal to IO omega 2. Okay, so we know that this is 0. So this will be 0 plus the integration of T1 is 0. It starts from 0. T2 is 4. Okay, T2 is 4. Okay, MO dt. So M here we have 3t square dt. Okay, put this in bracket, is equal to IO is 5.4 and omega 2 is the one that we want to find. Okay, omega 2 is the one that we want to find, the angular velocity. So now what we need to do is to integrate this. Okay, still remember integration? What do you get when you integrate 3t square? 3t square. What is the integration of 3t square? Anyone remember? The integration of 3t square. What is the answer?
T cube.
Sorry?
T cube.
3, sorry?
No, it's T cube.
T
T to the
cube,
power.
yes, T cube, exactly. So when you integrate 3t square, okay, so it becomes 3t to the power of 3 and then divided by 3, right? So 3 and 3 is gone. So what you have is 3 to the power of t to the power of 3. Okay, so now t to the power of 3, and you have the time from 0 to 4. Okay, so what you do is you put 4 in the equation, in the formula first. So this will be equal to 4 cube minus 0 cube. Okay, so first you put 4 in t and then you put 0 in t. So what we want here, what we get here is this 4 cube lah. 0 cube is equal to 0. So 4 to the power of 3. What is 4 to the power of 3? What do you get? 4 to the power of 3. Let's calculate. Where's my calculator? Okay, 4 to the power of 3 will give you 64. Okay, 4 to the power of 3 is equal to 64. So coming back to the principle of impulse and momentum here, so you will have 0 plus 64 is equal to 5.4 omega 2. Therefore, we will get the value of omega 2, which is equal to 64 divided by 5.4, and you will get 11.85. Okay, 11.85 radian per second. Okay, so that will be the final answer. All right, any question? Any question on that? Okay, there's no question. Let's move on to another example. Right, similar example, but this is general plane motion. Okay, if you can see that the wheel here rolls on the ground, but the wheel in the previous question is fixed at point O, so the wheel keeps on rotating at point O. But question number 2 here, it is general plane motion problem. The wheel will roll on the ground. So let's read the question. 300 kg wheel has a radius of gyration about its mass center KO 400 millimeter. Okay, again, this is the clue that this is a non-homogeneous. KO is used to calculate IG or IO in this case. Okay, the wheel is subjected to a couple moment. Okay, so there is a moment 300 Newton meter. What you want to determine is determine its angular velocity 6 seconds after starts from rest. This is another clue. And another clue is no slipping occur. Okay. And also you need to determine friction force. Friction force that develops between the wheel and the ground. Okay, so that those are the parameters that you need to find. Okay, so let's draw first the free body diagram of this wheel. So when the wheel is rotating, you will have the mg, which is pointing down. So this is mg. You will also have a normal force, NA, at the bottom. Okay, you have the 300 Newton meter moment here. This is also another force, and we also have the friction force. And because of the rolling of the wheel, the friction will be pointing to the right. Okay, so these are four forces that are currently acting on the wheel. Okay, so when it says no slipping occur, we know that the contact point here is basically the location of IC. Okay, so this is the location of IC. And because that contact point is the location of IC, we know that at point O pointing forward is basically, at point O pointing forward is basically the velocity of point O, VO or VG lah. In this case, VO. Okay. Okay. All right. So again, the question wants us to calculate the angular velocity, and this is another rolling problem. So what we need to use, it is not necessary that you use all three equations to solve the problem. Okay, it depends on the problem. So similar to the previous problem, we only need to use the third equation for this case lah. Okay, so let's use the third equation, which is IO in this case, IO omega 1 plus the integration of MO dt is equal to IO omega 2. Okay, so what we want to find is basically this omega 2 lah. Omega 2 is the one that we want to find. Okay, and looking at the question here, it says starts from rest. So you know that omega 1 equals to 0. Okay, so the first term is already equals to 0. Okay, now, this is not similar like the previous example. Previous example, the moment is changing with time because the moment is equal to 3t square. So there is a function of time there. T equals to 0, moment equals to 0. T equals to 1, moment equals to 3, and so on. Moment keeps increasing when the time is increasing. But this time, in this problem, you can see that m is equal to 300. So moment is fixed. So in this case, the integration becomes easier. The integration becomes easier because now the integration is integrating from 0 to 6 of 300. 300 is the moment, dt. Okay, what happens when you integrate 300 dt? What do you get? Anyone?
300t.
300t. Okay, 300t. So you get 300 times t. Okay, and what is the value of t? The value of t is, again, you have from 0 to 6. So you put in 6 there, minus you put in 0 at the t. So basically, this will give you 300 times 6 lah. 300 times 6, which will give you 1,800. Okay, 1,800. So that is the impulse. 1,800 is the impulse, MODT. Okay, so what we have not calculated here is the IO. So we need to calculate IO first. So IO is then equal to M times KO square. Okay, M is 300 kg. 300 kg. KO is 400. So you convert that to meter, it will give you 0.4 square. Okay, 300 times 0.4 square, which will give you 48 kg meter square. Right. Okay, so then we will substitute in the equation. We'll substitute in the equation. So we have 0 plus MODT is 1,800 equal to 48, IO is 48, omega 2, right? And therefore, we will then get the value of omega 2, which is equal to, wait. Oh, sorry. Sorry. I forgot that we have the friction. Okay, we have the friction. Okay, so again, I will erase this first. Okay, so let's focus on the free body diagram. So when we calculate the moment about point O, okay, so what we do is, like I show you in the class, we will draw a line at point G. Remember? So at point O in this case. So at point O. So whatever force that falls under that line, falls on that line, on the line that we draw, perpendicular, vertical and horizontal line, will not have moment. So in this case, NA has no moment about point O. MG also has no moment about point O. But we have the moment itself has moment. and also the friction. So we forgot about the friction. So we need to include the friction as well in this case. So we have the moment MODT is equal to 1,800. So this, we need to move this a little bit to the back to include the friction. Okay. So the friction here, to transform the friction into moment, you need to multiply with this distance. So let's use this color, this distance here, which is 0.6 lah, which is 0.6. Okay, so then if you look friction to go to point O, it will go this way, which is in the other direction of the rotation punya direction. Direction of rotation is clockwise, but the friction to go to point O, it will go in the anti-clockwise direction. So that will give you a negative moment. Okay, so that will give you a negative moment. So let's put in minus, sorry, we can put it here. So let's, okay, here. So MO minus minus FR times 0.6 dt. Okay, so this is the moment lah. So moment we have two. Okay, so one is MODT. We have settled that. MODT we get 1,800, but now we have FR, FR times 0.6 dt. So this is the same because we know friction is constant, not changing. So this will be equal to friction times 0.6 to make it the moment, and multiply with the time, which is 6 seconds. So multiply with 6 seconds. So we will get here 3.6, 0.6 times 6, you will get 3.6 FR. Okay, we don't know what is the value of friction force yet. Okay, so coming back to this equation here, right? So this equation will become 0 plus 0, IO omega 1 is equal to 0, 0 plus 1,800, and then minus 3.6 FR, okay, and then is equal to 48, IO is 48, and omega 2. Okay, so you can see here that we have two unknowns, which is FR is unknown, and also omega 2 is also unknown. So these are the two parameter or quantity that you need to find from the question here. Okay, if you zoom into the question, one, we need to calculate the angular velocity 6 seconds after, and also we need to calculate the friction force. Okay, so we have one equation here, but we cannot calculate, or we cannot solve, because we only have one equation, but we have two unknowns. So we need another equation. Before we proceed to another equation, let's rearrange this. Okay, this minus 3.6 FR, we can bring it to here, which it will become positive. So we will get 48 omega 2, 48 omega 2 plus, now it becomes plus 3.6 FR. So these are two parameters that we want to find, is equal to 1,800. So this is equation number 1. Okay. So because we cannot solve using only one equation, then we can go back to another two equations. So which one we can use to get another equation, so that we can solve simultaneous equation. Okay, by looking at this problem, we can use the x-axis equation, because the y-axis is there is no motion in y-axis, and the friction force is acting in x-axis, so that we can use the friction force lah. Okay, we can use the friction force. So let's write down the equation for x-axis. So we have m vx1 plus the total force in x-axis dt is equal to mvx2. Okay, vx1, we know this is equal to 0 because it starts from rest. When it starts from rest, everything equals to 0 initially. V1 equals to 0, omega 1 equals to 0, both equals to 0. Okay, so now what we need is fx dt. Okay, fx dt. So from here, the only force in x-axis is the friction. So therefore, it's the friction multiplied with 6 lah. Friction is Fr, yes, correct. Friction multiplied with 6 seconds, the time. So that will give you Fx dt is equal to m is 300. Okay, m is 300. But now we have Vx. We have now Vx2. Okay, Vx2, which we don't know. Vx2 is basically referring to VO. VO is Vx2 lah, because VO is the velocity of the wheel, and it only has velocity in x-axis. There is no velocity in y-axis because there is no motion in y-axis. So because of this IC location and VO, we know that we can use this as similar to rotation punya equation. So we can use Vx2 is equal to omega 2 times R. Okay, this comes from V equals to omega R. Okay, this equation is what we refer to get Vx2 equals to omega 2 times R. So the value of R we know, R is 0.6. So basically Vx2 is 0.6 omega 2. Okay, so now we can transform this equation to becomes 6Fr is equal to 300 times Vx2 now becomes 0.6 omega 2. So therefore we have 6Fr is equal to 300 times 0.6. We will get 180 omega 2. So we can rearrange this equation to get similar like this equation. Okay, we can put omega 2 in front. So you will have 180. Let's use a blue color. 180. Now omega 2. Okay, now we bring 6Fr to the right hand side. So it will become negative minus 6Fr. Right? Then it is equal to 0. So this will be our second equation. Right? So you can see that this is our first simultaneous equation, and this is our second simultaneous equation. We can now solve simultaneous equation. 48 omega 2 plus 3.6 Fr equal to 1800. And the second equation is 180 omega 2 minus 6 Fr equals to 0. So by solving this simultaneous equation, you will get omega 2. You will get omega 2 is equal to 11.54 radian per second. And you will get Fr is equal to 346.2 Newton. Okay, so that is the final answer lah for this question. All right, so basically in example number 2, you have seen that you need to use 2 equations to solve the problem. So we have access to 3 equations, not necessarily that you have to use all 3. For example number 1, you only use 1 equation, which is equation number 3, to solve the problem. But the example number 2, we have to use equation number 3 and equation number 1 to get 2 simultaneous equations. And when you solve simultaneous equation, you will get the value of omega and also the value of friction force. Okay, do you have any questions on this? Anyone has question before we end the class tonight? Any question? Okay, so if there's no question, that will be the end of our class tonight. Thank you for joining the class. I will share the recording in the WhatsApp group. So today we have covered the principle of impulse and momentum lah. So basically, what is important is that you know these three equations and you know when to use them. Not necessarily you have to use all three. It depends on the question. Sometimes you only use one equation. Sometimes you need to use two equations and solve simultaneous equations. Okay, if there's no question, thank you. That will be the end of the class. Probably we will next Monday. We do not have class next Monday because I need to go to KL. We will also have another replacement class online. I will inform later in the WhatsApp group when we will do the replacement class. And on Wednesday, we will have the class face-to-face where we will do quiz number 3 on Wednesday. So Wednesday will be the last class lah, of this subject, this course. And Thursday night, we will have test 3. All right. So that's all. If there's no question, thank you. And I will see you again in the next class, which I will inform later in the group. All right. Thank you. Assalamualaikum and have a good night.
Thank you.
Yes, sir.
Thank you, Doctor.
Terima kasih, Tuan.